So we've heard now about the theory that Paul has done on the KRB system at JILA. Now we're going to hear from an experimentalist, Bryce Gadway from Junior's group. He'll be telling us about how they're using that system to study the dynamics of long-range interacting spin systems.
Okay, great. Thank you, Wasim. I just want to start by thanking the organizers, especially the local organizers, Trey and Gretchen, for this opportunity to come talk to you about the research we're doing on ultra-cold molecules. And so this research is done at JILA, or JQI West. And it's a pretty big experimental and theoretical collaboration to make these experiments work. So it's co-led by Deborah Jin and Jun Yi, and then a great group of graduate students and former postdoc Bo Yan. And then over the years, we've had some really terrific theory support by a lot of people in the crowd. And currently, now that we're doing a lot of many-body physics, Anna Maria Ray, who's also at JILA, is helping us quite a bit. Okay, so this is a molecules session, and so I'll try to put the kind of research we do with molecules in perspective. So molecules are ubiquitous in nature. Some are very important to kind of chemical and biological processes. Things like molecular hydrogen are really important for astronomy and astrochemistry. But we're not really going to be doing any of these kinds of physics. We're going to be studying cold molecules. And there's also a really broad range of physics that you can study with cold molecules, including chemical reactions, fundamental physics, basically precision measurements of fundamental constants. We're also not going to be doing that kind of physics as well. We're going to be using cold molecules at extremely low temperatures to do many-body physics. And so basically, as Tillman was describing the other day, we're kind of in the field of Hamiltonian engineering. So Zoran had described making a flat box potential where you control kind of the distribution of chemical potential very well. Tillman had described control over kinetic energy terms. And there's a lot of really interesting single particle physics that you can do there. Questions of kind of localization and topology. But a lot of the really hard physics comes when you add interaction terms and you start to get correlations between particles in the system. So we're interested in engineering interactions between particles that basically can create non-local correlations in the system. And the cold molecules are not the only platform. There are many, many platforms with different advantages and disadvantages. But I'll be talking to you mainly about polar molecules and hopefully, leave you with a good impression of the advantages of this system. Great, so we'll be trying to build electric dipoles from the ground up. And so big chemically interesting molecules will not be what we're studying. They're a bit too complex for our needs. And then homonuclear molecules like rubidium-2 and cesium-2 are a little too simple for our needs. So we'll basically be looking for two atom molecules that can generate some charge disparity or charge asymmetry in the system. So if we do have a large internal charge asymmetry, basically in the frame of the molecule, it looks like there's an internal electric field. And if we get these molecules to low temperatures and align them in the lab, they'll interact like static dipoles. And this is a pretty nice system. It actually looks like little bar magnets that we're used to playing with as children. And so it's sort of intrinsically built for studying quantum magnetism. And as a tool for studying quantum magnetism, kind of condensed matter models, it's really nice to have an AMO platform in that we have a very well-defined microscopic description of the interactions in the system. We have a wide parameter control, wide control over the Hamiltonian, and we can easily study dynamic evolution in the system. And so the hope would be that an AMO realization of many interacting molecules can help shed some light on some kind of outstanding problems in other fields, and maybe detect new phases of matter that go beyond what's been seen in other systems. So a quick outline, I'll describe a little bit the toolbox we have at our disposal for studying many-body physics with cold molecules. Then I'll talk about how we make the molecules, some recent studies we've done on spin physics with cold molecules, and then a quick recap and some prospects for the future. Great, so at the single particle level, molecules are pretty interesting. They have many different internal degrees of freedom. So they support vibration in a linear molecule and rotational modes. So there's many internal states, and so you can think about studying systems well beyond kind of spin 1/2 particles. Like atoms, you have a large tunability, a large control over the molecules just with laser light or applying electric fields. And then also different microwave dressing and control with magnetic fields as well. But probably the most important thing is that the molecules have these two-body interactions at long range. So the fact that they act like kind of natural quantum magnets. And so there's actually a huge range of interactions that one can realize with molecules. Quadrupolar interactions, some correlated spin-orbit interactions that I'll maybe touch on a little briefly at the end. But I'll focus first on the ones that kind of emerge most naturally in a system and show up most strongly. So the first one encounters is a resonant spin exchange. And this is basically an electric dipole transition that happens between opposite parity states of the molecule. And so the states I'll be referring to specifically is one that's in its absolute ground state with zero rotation, and a molecule in an excited rotational state. And so we can address these transitions at microwave frequencies and with some small coupling between the nuclear quadrupole moment and the rotation of the molecules, there's actually splitting in this upper manifold, so we can spectroscopically pick out different transitions and realize what in effect is like a pseudo spin 1/2 type system. And then if we start with some configuration with two nearby spins of opposite parity, they'll actually realize just a resonant exchange where the excitation will move back and forth in the system. So this is great, and in terms of the kind of spin Hamiltonian that this realizes, it looks like an exchange Hamiltonian. And then there's this single particle energy term, which we can control either by a microwave detuning, applying an electric field, or optical fields as well. So this prefactor has this long range 1/r³ anisotropic scaling. And then the exchange coupling basically comes about due to the natural dipole moment of the species and the spacing between molecules. So for our system with KRB in a 1064 nanometer lattice, this is on the order of about 100 hertz. And then if you actually apply a large electric field and start aligning the molecules, you can induce icing type interactions. So this is where the eigenstates at high electric field are basically composed of contributions from opposite parity states. And so even if you have molecules in the same state, they have a non-zero dipole interaction between them. And so it looks like, as you'd expect from bar magnets, the energy of the system is raised if you have nearby poles aligned, or if they're anti-aligned, the energy is lowered. So in effect, with applied electric field, we have a really widely tunable Heisenberg XXZ model at our disposal. Where in the limits where one of these terms dominates, you have access to ferromagnetic and anti-ferromagnetic phases, a really natural kind of frustration due to the anisotropy of the interaction. And then in this kind of crossover region, it's pretty interesting. You get competing ordering along different spin directions, possibility for studying canted phases. And then one of the most appealing things about molecules is you have coherent tunneling, which is on the same order as the interaction strength. So you can really study kind of full models of itinerant magnetism. So this is really nice, but right now we're just doing basically the first studies with cold polar molecules. So we're going to try to isolate out a specific term in the Hamiltonian, and we'll not be studying itinerant models, and we'll also be working at zero electric field, where we'll basically be focusing in on this exchange interaction. Okay, so a bit of detail on how we make the ultra-cold molecules. Direct cooling of molecules is extremely hard, whether you're working with kind of molecules that are relevant to all of us, like caffeine, or even simple linear molecules like strontium fluoride. And for certain linear molecules, there's been great progress in recent years in direct laser cooling. But in general, you can't reach the kind of temperatures that we're trying to get to. They suffer from poor branching ratios, and given that, it's hard to reach the low capture velocities. And you'll hear something about this in the following talk. So we're going to take a much simpler approach, which is to make molecules from ultra-cold atoms. So basically, we do laser cooling on rubidium and fermionic potassium using techniques developed over the past few decades. And then at the end, once we reach ultra-cold temperatures, we're going to do a bit of chemistry to bind them into a molecule. So I'll skip over all the laser cooling and basically say at the start, we have an optically trapped degenerate mixture of rubidium and potassium. And so the first step, now that we have these very cold atoms, is to just initially pair them up. And for that, we use a Fano-Feshbach resonance like Paul was describing. We're basically, as a function of some control parameter in the lab, the magnetic field, we have an energy crossing between the free atom state and a molecular state. And if we go to the repulsive branch, we can cross over and realize this kind of first bound state of the molecule. And some coupling at this avoided crossing, or introduces an avoided crossing. And so sweeping slowly, we can adiabatically tune the system from free atoms into Feshbach molecules. And now the next step is to finally go to a ground state molecule, which has a significant charge asymmetry and a large dipole moment. There's a couple challenges here. There's a large energy gap between these two states, very poor wave function overlap, which is very important. And there's also many intermediate states. So this is not to scale, but between this initial Feshbach state and the actual ground state, there are about 100 vibrational levels, and each of these vibrational levels has many different rotational levels. So we really need a coherent process to move population from this initial state into the ground state. And for this, we drive a 2-photon Raman transition through an excited electronic state of the molecule. And we do this in a stirrup fashion so that it's adiabatic. And so these are two lasers coherently locked to a high finesse cavity. So in the lab, it basically looks like this. We start with an optically trapped Bose-Fermi mixture. We transfer atoms to a Feshbach state, and then we transfer them to the ground state of the molecules, and then we quickly remove the remaining atoms so as to avoid collisions and losses. And in the end, we have a cloud of something like 20 to 40,000 molecules at a few hundred nanokelvin temperatures, isolated in a specific state of the molecule. So this has been the state of kind of the art for quite some time, that we have a cold, nearly degenerate gas of fermionic molecules. And there's been a lot of effort to press to cool down the system to quantum degeneracy. However, this hasn't been attainable yet. There are several issues. One is that in the spin polarized Fermi gas of the molecules, there's been inefficient thermalization due to polyblocking. Now recently there's been a lot of great work in erbium that shows that if you go to large dipole moments, you can get effective thermalization even by mixing in higher partial waves. However, the main limitation is that our system is kind of intrinsically unstable due to these chemical reactions that Paul had discussed. So we observe fast loss in the timescale of a second due to exothermic chemical reactions. And this is fairly fast, but it's also several orders of magnitude faster if we're actually working with the kind of spin mixtures that are relevant to studying quantum magnetism. So our approach to getting around this is to actually just form the molecules in a deep 3D optical lattice so as to turn off tunneling and disallow the molecules from combining and chemically reacting. And here, we're limited to lifetimes on the order of a minute just by off-resonant light scattering. And so working in this deep lattice, this is one motivation to work in the limit of zero tunneling. Another motivation is the fact that we have a fairly high entropy gas of molecules, so low filling. We start with a few 100,000 atoms of each species and end up making about 20,000 molecules in the end. So there's probably no interesting physics to be seen due to kind of motional coherence of the system. Okay, hopefully this sets the stage for the kind of system that we have that we're studying. We have a low filling gas of molecules in an optical lattice. And now we're going to study dynamics that ensue after we quickly change the system to a state which is completely non-interacting, so a spin polarized gas, into some state that supports interactions due to these resonant dipolar exchanges. And then after we do this kind of sudden quench of the system, we're going to see how the correlations build up. And so I'll give you a simple picture that works at the pairwise level, which will actually be pretty relevant for our low filling. We start with some spin polarized gas, and then we do a coherent rotation of all the spins into an equal superposition of the ground and excited state. And now at this time, we have some combination of different triplet configurations, some which have no interaction under the exchange Hamiltonian, and some which would undergo these kind of exchange processes. And so these ones will be shifted in energy and acquire a phase shift. Now, no matter what time we measure the system, the net spin population is not going to be changing. So to actually see any interesting dynamics, we have to look at the coherences. So if we measure say the SX expectation value, this will just oscillate. So the two spins will reverse direction after some time, and when this phase is equal to pi over 2, they're actually maximally entangled. So this is what it looks like for two isolated spins. Now, in our system, we actually have about 20,000 molecules, many of them interacting at different angles and different distances. So what we'll end up seeing is coherent oscillations, but at many different non-commensurate frequencies. And if we look at the total signal, we expect to see basically oscillations and a decay. And so some high-frequency components that are picked out due to nearest neighbor molecules in the lattice, and then some large background of far distance pairs. Okay, so how we do the measurement? Okay, yeah. So basically, I've talked about the coherent interaction part of the Hamiltonian, and there's this other single particle energy contribution. Now this is fairly important. It will give rise to dephasing of the spins, and actually a suppression of spin exchange. And this you can think about if we have a system just spin polarized and locally excite one of the spins, it should be allowed to hop to any of the other spins in the system due to this long-range dipolar interaction. However, if there's a spin-dependent energy, inhomogeneous energy term, this will actually suppress transport to within this exchange bandwidth. So we have to take quite care to flatten out our potential for both spin states, and this means in our system changing the polarization of the light field so as to be at some magic polarization. And so in particular, we're very polarization dependent because we're working at zero electric field, and you can have energy offsets depending on whether the electric field of the light is aligned or anti-aligned with respect to the molecule orientation. So in particular for excited orbitals like the PZ, they can be strongly influenced by the polarization of the light field. These are plots of experimentally measured polarizabilities versus polarization angle, and depending on what states we're using, we can choose the polarization appropriately to maximize the coherence time. So we'll be working in a limit where the exchange coupling is much greater than this local inhomogeneity, but due to actually an intensity dependence of the polarizability, we'll be working in a limit where the global dephasing is greater than the exchange. And so in the experiment, we're going to try to probe the interactions using coherent Ramsey spectroscopy on these two spin states. We'll just do a global pi over 2 pulse to rotate all the spins to an equal superposition state, and then after some time do a readout pulse as well. And so if there's been no evolution of the spins, we'll just invert the population of the sample. However, during this whole time, we should expect some evolution, and if it's only due to this inhomogeneous, this single particle dephasing term, everything will be washed out given our large spread in energy. So to avoid this, we do a spin echo pulse in the center of the dynamics, which leaves the dipole-dipole interaction term unchanged. So we can, what we have left is dynamics driven by the interactions between the molecules. And we actually measure the spin coherence by rotating about different angles with this final pulse. And if we measure the spin dynamics without applying this echo, we see a very fast decay of the coherence. However, if we get rid of this single particle dephasing with a spin echo pulse, we see some pretty interesting dynamics. So we see a fairly long coherence time with some decay, and then we see pretty clear oscillations in the data. And these are occurring at a rate of 50 hertz. So in a good agreement for our expected interaction strength. And we can obtain more direct evidence for the dipolar nature of our interactions by basically stealing a technique from NMR studies, which have basically found ways to cancel out dipolar interactions in molecules for a long time. So this is the data that I showed before without spin echo and with spin echo. Now if we do a modified sequence that inserts extra pulses about an angle rotated 90 degrees with respect to the initial excitation, we actually see that the oscillations go away and there's a longer coherence time in the system. And there are many pulses here, but basically the single pulse is the most important. And it essentially acts like an echo for any pair of molecules that's interacting under this exchange Hamiltonian. So there's these two triplet configurations, one which has a phase shift, and this pi/2 pulse actually swaps population between these two configurations. Okay, so one nice tool that we have at our disposal to control the parameters of our Hamiltonian is a tunability over the dipole interaction strength. And we actually do this in a discrete way by choice of rotational states that we use. So I've showed data so far for the 1-1, but we can also excite to the 1-0 molecule. And so for the 1-1, it's pretty easy to think in a classical picture about how these molecules are interacting, that they're rotating about the quantization axis at about this rate of 2 gigahertz. And we in effect get the time average contribution of the dipole interaction. So at certain phases, they're side by side and have repulsive energy. At other phases, they're head to tail and have a negative energy. And if you average this over the whole cycle, it reduces the dipole strength by a factor of 1/2. In contrast to that, for the 1-0, we recover the full dipole moment. And so we can actually increase the interactions by a factor of 2. And so just looking at dynamics where we change this interaction strength by a factor of 2, you can see immediately that the loss of coherence happens much faster. And lastly, we have one last tool to study our system, which is we can change the density of molecules in a systematic fashion just using inelastic light scattering. And when we do this and go to lower and lower density, we see that the coherence time increases as you go to lower density samples. So there are some pretty clear trends. And one nice thing is that we have such a simple description of the Hamiltonian where we think, to a good approximation, it's purely driven by these exchange interactions. So since it's so simple, we can make direct comparisons to a fairly exact theory. This is a cluster expansion done in the group of Anna-Maria Ray, where instead of diagonalizing a system of 20,000 molecules, they diagonalize 20,000 systems of 10 molecules and then do a comparison to our data. And to note, they fix the density at a particular molecule number, then everything is scaled with this one fixed parameter. And overlaying the theory on the data, we find pretty excellent agreement with a good capturing of the oscillations and the decay in the data. So as an experimentalist, we can also just do a straightforward check, which is rescale the time axis by a factor of 2 to account for this difference in interaction energy. And when we do this and overlay the data, we also see basically a complete collapse of the spin coherence data for these different states. So this really drives home the point that all the interactions are being driven by or all the dynamics are being driven by interactions here. Great, and if we look again at the density dependence, we find a 1 / density scaling with the coherence time. And this is what we would expect for a 3D system with 1 / r³ interactions. Okay, so a quick recap and then maybe a few prospects on the future. This has been the first study of many body physics with cold molecules, and we realized a system of about 20,000 spins coherently interacting. There are a lot of things that one can study with cold polar molecules. One really interesting kind of innate interaction that shows up in a system are these correlated spin-orbit interactions. And this is unique to dipolar systems. So it's basically a quantum analog of or a cold atom analog of the Einstein-de Haas effect, where you have some chunk of ferromagnetic material, and if you either turn the magnetic field to 0 or reverse the sign, you can induce rotation in the material. So the magnetic domains will randomize, and the whole material will take up rotation. So with the interactions I showed before, we would never expect to see this. We're kind of trivially conserving the internal distribution of angular momentum. However, if we can control the degeneracy of these different rotational levels, we can actually get to a regime where another type of dipolar interaction takes place. This is one where an excitation will move in the system, but it will also change its flavor. And because there's a change in the internal angular momentum, there's actually a phase accrued, basically a dynamic varies phase that's accrued by this process. And so this will be interesting in future studies. The really interesting thing is that if you look a little bit at it, you can maybe think of ways to study dynamical gauge fields using this two-body interaction. So lastly, sort of all these studies would be benefited by working at a higher density of our molecules in the system. So we basically make our molecules by starting from an atomic sample and then converting every site that has 1 rubidium and 1 potassium into a molecule. Typical conditions, a few 100,000 atoms, making about 20,000 molecules. And we know that these are too many rubidium atoms to be supported in an n equals 1 Mott domain in our system. So lately we've been going to very large population imbalance. And at very low rubidium numbers, we find some pretty drastic increases in the conversion efficiency for the number of molecules we make per rubidium. So hopefully we'll find good evidence for high molecule filling soon. Great, and that's about it. But some excitement about all the new molecule experiments coming on in the field, which I think is the really interesting thing about this field of using cold molecules as a quantum simulator, just more diversity and plurality of species and groups. Great, thanks.
Thank you very much, Bryce. We'll take some questions.
Bryce, of course, this low filling factor might be considered as obstacle, and it is clear that it's good to go to low entropy gas with higher filling. But at the same time, what you have is a model of spin glass, quantum spin glass, because the guys are in random positions. They have attractive or interactive or ferro-antiferro interactions, so it's just a perfect model of spin glass. Has anybody studied the low energy physics for this kind of thing? And
so I think some really interesting observations could be made if we could actually access correlation functions for a spin glass like this. And start from some non-equilibrium spin distribution and see how actual spin transport evolves. So there are prospects coming on in the next few months for a next generation of the apparatus that allows for very high quality imaging and local manipulation of the spin. So yes, even at the current fillings, that would be a very interesting route to pursue.
Bill?
So I want to make sure I understand exactly what's happening in this spin exchange situation that you're talking about. Now you're talking about having a lattice that is so deep that there really is no tunneling.
Yes.
And you really mean really no tunneling.
Yes.
So that means, if I've understood correctly, that the quantum statistics, that is, whether they're fermions or bosons, is irrelevant.
It's irrelevant.
It's only the matter of the long range. Okay, so I mean, the thing was, lots of times when people talk about exchange, they mean that exactly it's the statistics that are driving the thing. But in this case, you're talking about just the long range.
So it's quite different than the exchange study in trace group. This is a direct sort of, it looks like a spin exchange process, but it's directly mediated by the dipole interactions between the molecules.
Okay, super. Now, now I've got a real question. So these things are wonderful models of magnetism, but of course they're electric. Can you imagine any circumstance where that matters?
I mean, formally at the Hamiltonian level, it looks quite exact to models of quantum magnetism. So I don't necessarily see any places that would pop up where it'd be quite different.
Your KBA, the molecules, they dissociate into the rubidium and potassium diatomic molecules because it's an exothermic reaction. What if in a particular cycle of the experiment, you increase the temperature and suppress this dissociation because of Le Chatelier's principle? Is it possible?
So we could certainly work at much higher temperature with lower loss rates, but we would have no access to the interesting physics that occurs at high density in the end. So we have to access these very low temperature, high density regimes to do the physics we're interested in doing.
Okay.
Actually, the frequency you observe in these oscillations, is that the most likely frequency? I mean, you have different coupling strengths in the, different directions over different length scales. If you Fourier transform the data, you see different peaks for
the
different coupling strengths
the direct
or
numerical Fourier transform of the data is not as nice as you may expect. But we do find strong evidence for actually the 3 strongest frequencies. So the nearest neighbor J of molecules aligned head to tail, and then that factor reduced by square root of 0.5 and 0.5.
When we combine the localized spin model and the internet spin model to get a universal spin model. In the localized spin model, it's like the Heisenberg model is spin localize the space. In the internet spin model, it's such as the TJ model, Hubbard model. It's the electron atomic just moving in the Bloch band.
This would be the actual molecule tunneling.
Yeah. I mean, says maybe we can combine 2 models that the universe one model.
I mean, certainly all the physics that appears in the just localized Heisenberg model is some limit of a model which supports tunneling and would also support unit occupancy. There are a lot of open questions with the TJ model and whether this may lead to something like high temperature superconductivity. And so that's definitely a really interesting route to go to combine coherent tunneling of the molecules and these long range interactions.
Let's thank Bryce again. Right, so Bryce seemed to be hesitant about cooling caffeine and ammonia. I think the next speaker will try to convince us otherwise.